Today I want to talk about subculturing cells. And when we do this in tissue engineering, when we're trying to build up a stock culture of cells for experiments, so imagine needing like 12 replicates for something that you're working on. First, let's talk about a little bit of vocabulary here. So passaging is when we detach those cells from their home in their current flask, and then we split them into multiple cell culture flasks so that we can bump up those numbers for future experiments. Confluency is how we talk about the number of cells and how much space they're covering. So in that figure here, this on the left-hand side is muscle cells at about 50% confluency. It isn't a very specific measurement, and we wouldn't use it for any sort of quantitative data. It's more of a qualitative measurement that we make basing just from experience. And so on the right-hand side, you can see these cells have filled and proliferated to cover the entirety of the cell flask. And they're even starting to differentiate. You can see them forming longer tubules. Trypan blue is a live dead stain that we use to count cells, and you'll see more of that in a second. And viability is an assay we run, and it's quantitative. We count so that we can have, it's kind of a measure of overall cell culture health. So when we're counting cells, we use something called a hemocytometer, which literally means cell counter. And this counting grid from that left-hand picture A is blown up in that image here. And so there's 4 boxes, C, D, E, and F, and those are the areas that we would count. And you can see on the bottom that it has some cell touching the top ruling equals in. And this is essentially just a guideline for you. So maybe there are cells all over the edges of your counter, and that happens fairly frequently. And so as a guideline, you count either the top and the right as in and the bottom and the left as out, just to kind of average that out. And it doesn't matter which you choose, you just need to pick 2 sides that you'll count in. So the way that we view the cells when we're doing the counting is with a trypan blue exclusion assay. And you can see these cells here in white, and then the pointed at images are in blue. And those ones are the dead cells stained with trypan blue. And the way trypan blue works is it enters through holes in the cell membrane to stain the interior of the cell. And so that's why you can't see it in live cells. When we talk about culture viability, remember it's a quantitative assay, so viability we get in a percentage, and it's just the number of living cells, so those white ones, divided by the total number of cells, the living plus dead. So you can imagine an example of 39 live cells, 42 total cells, and the viability would give us 0.928 or 92%. And this is good. We're looking for something above about 80% viability, and that's when we know that our culture is doing pretty well. When we talk about cell density, this is basically saying how many cells have we grown per milliliter. And so you can see on the bottom that it's a 1 millimeter by 1 millimeter square that we're counting within. And we pipette 20 microliters of cell stock into those chambers, and it's pretty specific. Hemocytometers are designed for this so that the math will work out. So cells per mil, we use the average cell count and multiply by the dilution factor. So you can imagine putting in like 50 milliliters of cell stock and 50 milliliters of trypan blue. So that's a 1-to-1 dilution. And then multiply by 10 to the 4th to get rid of that bottom 10 to the minus 4th centimeter cubed here. So for our previous example, if we use 39 as the average cell count, we'll multiply by 2, since it was a 1-to-1 dilution, and then multiply by 10 to the 4th to get 7.8 times 10 to the 5th cells per milliliter as our cell density, or concentration. So when we're determining how many new cultures we can make, we use the dilution factor formula here. So we use C1V1 equals C2V2, and so we're looking at concentration of the stock times the volume of the stock. That's what we passaged. Needs to be equal to the concentration of the new flask and the volume of the new flasks we're making. So in that example, we would have the 7.8 times 10 to the 5th cells per mil as our concentration stock, and we're looking to see how much of that stock volume we need to add to fresh media for the new cultures. And for muscle cells, we typically use 1 times 10 to the 4th cells per mil, but it varies based on the cell type, so check protocols. And a volume of a new flask could be something like 7 mils. And that gives us about 0.9 milliliters of the new volume that we'll add into the fresh media. So we'll do that, the 0.89 mils of stock, so that's with the cells that we counted, plus the 6.1 mils of fresh media. And those go together into a cell culture flask. And both of those are placed into the incubator at 37 degrees C with 5% CO2. And that's it, you've subcultured cells.